Hello, I am Prabhati, the professor for Data 645, the graduate machine learning course. This is an overview of the lecture notes for Unit 1 and Unit 2, Data and Pre-Processing. So here is the outline, data, attributes of data, data characteristics. We're going to discuss about how you measure data quality, and we're going to touch on the various data pre-processing types before you do any modeling, including aggregation, doing some sampling, dimension reduction, selecting features, creating features, how you discretize some variables, and transformation. So what is data? Now there's different way of explaining what data is, but in general, typically the way we understand data is it's a collection of records or a collection of some type of objects, and that record will have attributes explaining or describing each individual record. So the records are the objects in this graph shown, in this chart shown vertically as objects, and each one of those objects has attributes. Okay, attributes are the characters by which we explain the different aspects of the object or the record. So examples, eye color. If your objects are individuals, eye color could be one attribute of that. Let's say if your set of records are daily weather, temperature could be one aspect of attribute, explaining the weather. There are other names for attributes. It is also called variables, field if you come from database environment, could be characteristics or feature. Machine learning terms, popular machine learning term used for variables or features. And the collection of attributes describe the object. So let's say if you have 10 attributes explaining the object, collectively those 10 in that data set, those 10 attributes explain or describe each object. And similar to attributes, objects can also be explained with other names, as records, as point, as a case. That's typical in spreadsheets. It's also used. Sample is another name used. Entity or instances. Those are all names used for records or objects. Attribute values, so those are instantiation of the attribute. So those are actual values for each individual objects or records for that particular attribute. So it could be assigned numbers, could be symbols, depending on the type of the attribute and the appropriate value assigned to that attribute. An attribute can be mapped to different values or units. So age can be measured in months or years. So there's a different way of measuring the same thing using different units. And different attributes might also take same set of values, right? So examples is distance and height can be integers, right? And properties of attributes can also be different constraints. Sometimes there is a reasonable bounds for some attributes. For instance, height, you have to bound it with some max and min values, otherwise, it doesn't make sense, right? So there is reasonable values and limitation put around that based on the type of attributes. So those are attribute values. Types of attributes, in general, there are two different categories. Those are broad categories, qualitative and quantitative. Qualitative are subjective, in general are text-based, and description of qualitatively describing something. Quantitative are more objective. They're in general numbers of some type. So for the qualitative, here shown 3 different types: nominal, ID, name, unique ID, zip codes, colors. These are qualitative descriptions. And ordinal are some logical ranking of things: tall, medium, short. There's no numerical values, but there is logical ordering. Cold, warm, and hot is the same thing. And another one is binary. It takes 2 values, 1 or 0, yes or no, some dichotomous values. And quantitative are generally numbers, could be continuous, that could take infinite number of possibilities, distance, the speed, and energy. Discrete is still numbers, but they're bounded with some range. So here, result of rolling a die, right? There is some possible outcomes, like 6 different values. Number of inventory items. There is finite in general. And intervals are for calendar days and temperature. So if you take interval values, those are also numbers, but it's a different way of explaining numerical values. So generally, 2 different broad categories, qualitative and quantitative, and we deal with this kind of attributes all the time in machine learning. Some machine learning models can directly leverage qualitative inputs, but mostly they are represented through some kind of transformation. So how do we represent discrete and continuous variables in the computer? So as we say, discrete attributes has only finite elements or a countable set of values, and we represent them as integer variables. Binary attributes are a special case of discrete attributes. So binary means 2, it's countable, it's just a type of discrete variable. Continuous attributes, on the other hand, has real numbers and contain infinite possible values, and they are represented in the computer using a finite number of digits in the computer. There is no true way of representing real numbers in the computer, so there's simplification. They are typically represented as floating point variables. Okay, types and characteristics of data. So record data is the one that we saw earlier. Typically matrix type. It consists of collection of records or objects that are each has attributes or variables representing or explaining some aspect of that object. Transactional data is also record data, and also documents. A set of documents are record data. Another type is commonly used. One is graph data, and those are represented by nodes and edges. The edges connect the nodes. Some examples are the World Wide Web, molecular structure, and social networks, and let's say friends that you follow, or for instance on Facebook, your friends are nodes, and the different connections that they have are represented by edges. So those are graph data. And order data is it maintains a relative ordering, so the order in which the data is represented is important. Some examples of that is spatial data, temporal data, sequential data, so those in genetic sequences. Those are some examples of order data. Some characteristics of data is dimensionality is an important aspect of data. There is this term in statistics called curse of dimensionality, as you have a lot of attributes explaining the data in the way you represent that in the computer. So sometimes modeling becomes difficult. Okay, so that's called curse of dimensionality. So the dimension is important, as you have a larger number of attributes explaining the object. Uh, so represent that in computers becomes more challenging. Sparsity is the actual values. If you have a lot of missing values, you could have many attributes, but if a large number of them are actually missing, so that means you have sparse data. Resolution is a scale at which the data is represented, right? Some kind, there is small units, large units, so those are resolutions. Another important element in data analysis in general is data quality, and data quality can be explained in different ways. So noise is one important aspect of it. So if you have erroneous values, uh, example, distortion of voice when taking on a poor phone is an example of that. So if you have noise in the data analysis becomes difficult because you have to separate the noise from the signal or the true values. Outliers is another important data quality issue. If you have now some modeling techniques, learning algorithm are affected more than others. For instance, regression is affected much by outliers. So these are considerably different values from the typical values in the data. Okay, those are outliers. Important to treat those. Missing is another issue of data quality. So if you have missing values in a number of attributes that describe your record or your object, that's another issue, right? Similar to outliers, some algorithms are affected more than others by the presence of missing values. And there are some ways to deal with it, and then we will cover uh, in data pre-processing that how we treat missing values, typical values, and then how does it affect the different algorithms. And duplicates is another one. This is effectively you are having the same values for different objects or identical in some sort. Typically that's caused by if you have different sources and you are merging the data, and if there is no good way of deduplicating, then you will be having duplication issue. So that's another important data quality aspect. Here are some data pre-processing. As I said earlier, it's a very important aspect. So data exploration involves data pre-processing. So once you do exploration, have some understanding about distribution of variables and nature of the data, type of data, if there are any correlation, you leverage visualization, and then informed by that knowledge, then you will have to go through data pre-processing as required. Again, this is also dependent on the type of analysis you'll be performing and the learning algorithm you'll be employing. But generally, these are the type of data pre-processing we do. Aggregation, so this is some way of combining multiple variables or summarizing variables. Sampling is taking a subset of it. Sometimes if you have a large number of variables, you may need to reduce dimensionality. And similar to that, sometimes you have to select a subset of the features or the variables in the data, and sometimes you need to create new ones through transformation or maybe some kind of applying some function. And discretization and binarization are another one. It's an important type. This is depending on the algorithm employed, some algorithms cannot directly handle numbers, so you might need to describe those. And attribute transformation is also transforming variables into different form, from maybe functional form or also through another type of transformation. So aggregation, that is a way to combine two or more attributes into a single attribute to perform analysis or to simplify our analysis. Now, aggregation can be used for data reduction. So as you combine attributes, you will be having less number of attributes. So that is, one way of reducing the size of the data. Sometimes you can leverage aggregation for changing the scale of the variables. For instance, cities can be aggregated into regions, states, or counties. Okay. And also sometimes you may need to aggregate data for more stable output. If you have a lot of variability in the data, when you aggregate that, the variability or the variation that could be reduced, and that give rise to stability. So aggregation is a simple type of data pre-processing. So sampling is another important type of data pre-processing. It is a selection technique. So usually you won't be able to get data from the entire universe of the domain which you're performing the analysis. It's just not practical, it's very expensive and time consuming. And it's not necessary, especially for some of the latest techniques that we employ in machine learning. The key principle for performing sampling is you have to make sure that it is representing the domain that you're performing the analysis. So it has to be a representative sample or a good approximation of the entire data set. Okay. Another one is a sample is representative. It has approximately the same property as original data set. So yeah, it's just the same way of saying the first bullet where it has to represent the domain. So yes, and then that means both in terms of the way you perform the sampling as well the number of samples that are included in the analysis. So sampling is important. There is science behind performing sampling. There are different kinds. Types of sampling. So a simple random sampling is a simple type selecting technique where you have equal probability of selecting any particular object or record. Okay. And sampling without replacement is, so at each iteration you select an object and that object is not replaced back to the universe from which you taken sampling, so it can only be selected once. And the other one is with a replacement. You take a sampling and then the sample you have taken is put back in the universe again in the population. So that means there is a chance that you could select that same object again. So that is with replacement. And stratifying sampling is a technique where you create different partition by some category, and then you take proportional representation of samples from each of those groups or from the stratified groups. So these are some common types of sampling. Sample size is an important aspect of sampling. Earlier, I said that one way of measuring your samples or an important element is the sample size. And the way that whether the sample is representing the domain or the population is one element of that is size. Okay, so it has to be large enough to represent the population, and usually as you have larger samples, it increases the precision of the estimation of whatever parameter that you're estimating. The larger sample you have, in general, the more confidence you'll have. If it is too small, it might not sufficiently represent the domain or the population. And of course, Partly the sample size is determined by how costly it is to gain or to obtain the sample. There are different ways of determining that or choosing samples. Experience could be one. If you have some kind of domain expertise, then you can make judgment of or leverage your experience about the sample size, what sample size you need to have, and the variation that's represent the target variable. If you have a target variable and the variance could be that could be used, could be leveraged to determine the sample size. You can perform some statistical test whether you have sufficient sample size as well, and then similar to that is confidence level. You can determine different confidence level proportional to the sample size you have. So these are different techniques of determining sample size, but sample size is important because that is one element of measuring a representation of the samples of the population. Another important element of data analysis and data pre-processing involves dimensionality. And I mentioned earlier, curse of dimensionality. This is a phrase in general used in a statistical analysis that describes a situation where when you have a large number of dimension representing that sufficiently in computers is difficult. Any amount of data needed to fully represent is also higher. Large amount of data is needed. So as dimension of data increases, the amount of the data that to perform accurate analysis increases. Otherwise, if you don't have sufficiently large amount of instantiation, then you don't have sufficient data. It becomes too sparse, too fragmented. So it's a big problem. So this graph shows a situation where if you have a large number of attributes or large number of or high dimensional data, even records that are close to each other in reality becomes too far away. And so this is an aspect of data analysis that now latest algorithm actually can leverage high dimensional data, assuming there's sufficient values for them. But representation in memory, computer memory, becomes challenging as well. So how do we deal with dimensionality? So dimensionality reduction is one technique by which we mitigate curse of dimensionality. If you reduce the amount of attributes or the number of attributes that represent the data through some transformation, then you will be dealing with a smaller number of dimensions. So that mitigates the curse of dimensionality issue. Another reason is if you can sufficiently represent the large number of attributes with a smaller number, then you have less of memory issue, and data representation and memory becomes easier for data mining algorithm. Also, the iteration, the number of permutation you need to perform might be easier or smaller. As a result, the computing resources required will be less. And visualization, when you have a small number of dimensions, variables, it's easier to visualize the data. And sometimes just because you have a larger number of variables doesn't mean that you have all of them equally important. So some variables might carry a lot of noise. So this technique of reduction can actually be used to eliminate or remove variables that are less relevant for the data analysis. And some techniques, a very common one is principal component analysis, PCA. Another one is singular value decomposition. And there are also some supervised and linear techniques to do dimensionality reduction. PCA, the principal component analysis method, is a common technique for dimensionality reduction. It is a technique at a high level. You find the dimension in which the variation is the largest, and so you do the transformation or projection of the variables into that, and so a large number of the variations already represented. So that means you don't need the other variables as many. So you could represent with 3 or 4 components as the entire data set by finding uh, the the component that captures a larger amount of the variation. So, in a high level description of the feature at that. So, it is a very widely used technique for dimensionality reduction. Another data pre-processing technique is feature subset selection, and there are different types. So the brute force method is a way that you just consider all possible combination of the features, and so the data mining algorithm, whatever learning algorithm, will be considered all that possible features. That's a brute force method. Uh, Unless you have a small number of features, it is not practical. Another one is embedded. There are some learning algorithms or data mining techniques that naturally part of the algorithm go through data selection process. So it try to optimize the number of features that it uses that are relevant for the algorithm that is being employed, and these are embedded, just part of the learning algorithm. There are filters. Filters is before you run the algorithm, you run some feature technique or a scheme to select a subset of the features that are more relevant or that represent the variation of data more insufficient for the data learning algorithms. And another one is wrapper approach. That is, as part of the learning algorithms, is determining the the features that are important, but that is part of the learning algorithm itself, and you don't even know exactly the features that are selected. It's just an integral part of the learning algorithm. Learning or feeding the data go through the features that are more relevant. So it you're not, unlike the filter method where you select the features and you input those features to the learning algorithm. This one, as part of the learning itself, is down selecting the features that are more relevant. Another data pre-processing technique is feature creation. So this is a way to create new attributes that was not captured as part of the data collection. So this will enrich the data in some way, and could be done in different ways. There are 3 general approaches to do that. Feature extraction. These are creating new variables based on domain expertise. So if you have some domain specific criteria and understanding, you can formulate or extract new variables or new attributes. Now, this could also lead to errors in subjectivity, but it's just one way of extracting or creating the methods. Another one is mapping to data into new space. For instance, you can transform through some kind of functional transformation. If you take, let's say, log or square root, so you're creating a new variables through the function transformation, or by taking into a newer space. Let's say you have a smaller number of dimension, you can transform into a higher dimensional space, and that will create new features in that new space. And it's called mapping data into new space. And another one is you construct from existing ones. So you can come up, some clever of combining multiple features into newer ones. Okay. There are some variation of this as well, but these are the general method, the common methods of creating new features. Another very important data preprocessing technique is discretization. This is a way to transform continuous attributes, numerical variables, into discrete outcomes. There are many reasons why you need to do discretization. Some algorithms, for instance, association mining or creating association rules, it doesn't work with numerical values, direct numbers. So you have to do some kind of transformation or discretization into discrete values. So discrete means some kind of contiguous intervals. You create into contiguous intervals. Uh, uh, just some logical grouping into discrete outcomes. There are many different methods. These are some of the common ones. You can discretize by equal frequency. That means each group in the discrete outcome will have the same number of frequency. And then you can equal weights. That means each group will have the same distance or equal weight regardless of the number of frequencies, the number of attribute records that fall into that category. K-means based is another discretization technique. K-means is a type of unsupervised learning and clustering. And there's also decision tree based type of discretization. We will cover all this technique when we do our pre-processing and throughout all our assignments, because pre-processing is an integral part of performing any data analysis and model fitting. But discretization is a very, very important type of data processing, data pre-processing. Last but not least is variable transformation or attribute transformation. This is mapping of existing values to new ones, replacement values. So usually done before you fit your supervised or unsupervised model. And for continuous attributes, as I mentioned earlier, functional transformation. Let's say if you take the power of the values of the attribute or log, square root, any other functions, that is, transformation using functional functions. And also standardization and normalization, putting into some scale between min and max values. That's also a type of transformation. Those are for continuous variables, and for categorical attributes, you can use encoding. One hot encoding is a common one. You can create labels for each, and also could be based on frequency. Feature hashing is also another type of transforming categorical variables. Okay, that is the end of the lecture for Unit 1 and Unit 2. We will cover all this topic in class in detail and practice them when we fit our models and work on the quizzes. Thank you for your time and see you in the class.